It's going to be, I guess, week 2 or 3. Well, this is level 2 now. So we're past last week we looked at Arduino on a relatively larger scale, and we looked at the different inputs and outputs. We saw digital, we looked into PWM, and then on this side we had a look at analog, um, and the general power inputs and outputs. This week we're gonna miniaturize that a little further and look into this AtTiny85. This is the Atmel Tiny series, and it has small memory. It has 6 IOs, and you can see that this has 3 power pins over here, which is voltage in or 5-volt out, ground in. So you can connect, if you want to connect this to a battery, you will be connecting the ground and the V in. So then you have LM05. This is a 5-volt regulator. What this does is that you can put any kind of voltage that is 6, 7, 8 volts, 10 volts, 12 volts at these 2 pins, and it's going to step it down to 5 volts, which you can get out of pin 5. And also that same 5 volts is what powers your microcontroller over here. So when you say digital high, each of these pins is going to put out 5 volts. Okay, so here we can see these are the 6 IOs that is connected to this. So there are 8 pins on this microcontroller AtTiny85. 2 of them are positive and negative, so one's positive and one's negative, and the other 6, 1, 2, 3, 4, 5, 6, they're connected over here to from P0 all the way to P5. Installing this device was a bit tricky, and I'm going to attach a few links to how you can go about installing it. You have to go to this website, DigiSpark, and from there you have to download a few drivers and install the drivers, install the board onto your Mac or PC, and then once you plug it in, it should work. Now what's tricky about this or about these small AtTiny microcontrollers is that you can program them in 2 different ways. You can either plug this into the USB and program it like that, or you can use another Arduino to program this. So before today, the way I used to program this would be to use, I would solder 6 pins from here to these, and then you can program or like burn a bootloader onto this. But now I think you can just plug this into the USB and program it as well. So the way that this works with the USB is that the moment you plug it in, you have about 5 seconds to load the program, and after that the chip goes into whatever's loaded in the pins mode, because 2 of these pins are connected to the USB. So you can't upload a program and run the program at the same time. So there's a phase during which the upload happens, and then right after that, the program runs. So as soon as I plug this in, I have a time bracket over which I can upload the program. And then a few seconds later, you can see that the actual program of the microcontroller running. And during that time, you can't upload a program to this. So let's go about and see how we can upload our first program. There's an onboard LED that is connected to pin 0, or I think it's pin 1. And on the board, on the Arduino IDE, as soon as we say, as soon as we give it instructions to put that pin high, that red LED on there should start flashing. Okay, let's see how we can do that. So this is the website DigiSpark. This is the device. This you will find in the Excel sheet for all the parts. And here is the digistump.com, where you can see the same board. And then in resources, you have to download this. On the download page, you want to download this. Let's see it load. You have to follow these instructions. It says software, you need to have Arduino IDE. So first of all, you download Arduino, which I'm assuming you guys have by now already. You download, unzip, and install DPINS64, or like follow this YouTube video, and that's the link. It just downloads it. Install or unzip Arduino, run the application. In the Arduino application, go to the preferences, copy this link to add the board, click OK. You will find your board. And in fact, before you upload any kind of software on it, you want to go and follow this video that they've linked on this website over here, this link up here with the YouTube shown in this YouTube video. So if I open up this, it's gonna take me to that video. You can follow this video and it's going to show you how to debug the driver install for this device. Once you're through with all of that, you don't need any of these anymore. And we're going to just get into the Arduino bit of this. So let's go to Arduino, load this up. Tools. So in board, it's pre-selected, but once you add the boards from board manager, you can scroll down and here you will see DigiSpark default 16.5 megahertz. You select that and that's it, your board selected. I'm going to paste my program here, which is defining pin 0 and 1 as output, and then writing high, giving a delay, and then writing low, and then giving a delay. So it's a 1 second on, 1 second off, and it's doing it to 2 pins, so 0 and 1. I think let's comment out pin 0, because I think this is pin 1. LED 1 on the board. And the way to upload this is that you don't plug the device in, you first hit upload, and it will say plug in the device now. So you have a few seconds to do that, 60 seconds. Plug it in, and then it gets automatically detected and unplugged. So it's it gets virtually unplugged. So right now your USB is giving power to this board, but it's not communicating with the board. So you can see that you have one of the LEDs blinking, the red LED, and that's pin 1. And out of these 6, we can find out which one that is by connecting our multimeter. Multimeter is 1 pin to ground, and the other pin, let's try pin 0. So it's not pin 0, it's actually P1. Is it? Yeah, it's P1. It goes to 5 and then 0. 5, 0, 5, 0. So it's P1. Okay. Cool. So P1 on this board is connected to an onboard LED. So you can kind of debug and see how things, if your program checks out. All right, that's step 1. Hey there, guys. So we're now going to move into the second stage of our miniaturization, where we look at power management. So all devices consume power, and some of them consume less than others. For instance, a microcontroller's power consumption, I mean, depending on the microcontroller, let's take this one, is about a few milliamps, and a sensor like this is usually ranges in microamps. A motor, on the other hand, is a few hundred milliamps. So this one's about 80 milliamps, and the servo that we were playing with last week is rated at 100 or 200 milliamps, probably even more. So things that are mechanical end up using more energy. LEDs are usually within 5 milliamps. But as you increase the size of the LED, and if you cascade many LEDs together, you're going to have to add up all of the power consumption of those LEDs and make sure that your battery or whatever power source you're using can deliver that kind of energy. Now, as we're looking into wearables, we want to keep things really sleek and low profile. That's why we're moving towards miniaturization, and we're playing with small chips, and we'd be moving to even smaller ones. When it comes to power consumption, you're usually limited by how much energy you can store in a battery with a really slim form factor. Like one over here says 25 milliamp hours. What this means is that this battery can run an LED, and if this LED is consuming, let's say, 5 milliamps, if this LED consumes 5 milliamps and runs at 3 volts, and this is giving you 3 volts and 25 milliamps, you can do the division, and turns out you could run this LED for 5 hours. If you could do a small math session on power consumption, and hopefully it's going to come in handy for a while. So how power works is that power is usually comprised of voltage, and ampere. So all power sources and pretty much all systems, all electronic systems, all data sheets will always provide you with these two numbers, and that's usually the first numbers you look into when you're selecting a sensor, when you're selecting a microcontroller, when you're selecting a power source, or when you're selecting any kind of interface. Where did that go? Here we go. Any kind of interface. This is some power management board. And what this board will do is it'll take in solar energy and it'll store it into the battery. And if and when you need it, it will output it to the USB, or it will power your electronic boards. So how you do this is you make sure that all the voltage, so that the voltages between the devices are compatible. Whenever you're looking at microcontrollers, you have to see what's their input range. Some would go up from 2 volts to 5.5 volts, but other microcontrollers, like this one over here, so much powerful one. This one goes from 1.2 to 3.6. So you can't feed this 5 volts and expect it to work. So you need a step down converter that will convert 5 volts to either 3.0 or 3.3. Both work. They're both under 3.6. But how I go about this is I first define my system. I'm like, okay, in this device, I want there to be a microcontroller. I want there to be a bunch of LEDs. I want there to be a motor. Where did that motor go? Okay, I want there to be a vibration motor, and I want there to be a touch input sensor, which is over here. And then I look at each one's spec sheet. I look at the data sheets, and I find out, so this motor runs at 3 volts. This one runs at 2.9. So things that say 2.9 or 3.1, they pretty much work with 3. This works between 3 and between 1.2 and 3.6. And so now I have a rough idea, knowing that the voltage that I should stick around ranges between 2.9, 2.8 to 3.1. So 3 volts is what I'm going to select. So this is the voltage that all of my components are going to work with. But then you realize that, well, my lithium battery says it's 3.7 and it has 25 milliamps, 25 milliamp hour capacity. We'll go in a bit what the capacity is all about. But how these systems work is that if you have 3.7, so it's not going to be 3.7 is nominal voltage, means it's about 40-50% voltage, 60% voltage. Lithium ions, when you charge them up to max, they go to 4.2 volts. So that's your problem. You can't feed 4.2 volts into this when your battery is 100% charged. And then when they're discharged, this number goes down to 3.2 volts. So this is full, and this is when your battery is empty. So what you want to devise is a intermediate. What you want to put together is an intermediate device that no matter what voltage you put inside it, it will always give you an output of 3 volts. So this is your device. It will always give you an output of 3 volts, and you have an input range of high value of 4 point whatever. You have a high value of anything, and then a low value of 3 volts. So whenever we put in 4.2, it will still give out 3, and then everything in between up until 3.2 volts, this thing will put out 3 volts. This device is called an LDO, or you can also use buck converters, BUCK converter, and LDO stands for LDO. How can I forget that? I forgot what it stands for. So LDO electronics. Low dropout regulator. So low dropout means that this device itself consumes less energy. And so what it does is between the input and the output, it can give you any kind of voltage range. To give you guys an idea of what these LDO chips look like, so I have one here. These chips are you can get them in really small sizes. This one's a really cool one. I think it does from 18 volts. So this is how small it is. This is an 18 volt LDO. Super tiny. It's, I think, 2 mm by 2 mm. You can see it has that dot in one corner that tells you what's the orientation of the chip. On the back side, you have a few pins, and then in the data sheet of this, you can see what these pins, what you need to connect to these pins. So from what I remember, so that notch, that cut notch on the top means that's where you need to start counting. So that's pin 1, 2, 3, and then jump over 4, 5, and 6. So you connect one of them to the ground, that's your common ground. Then you connect one of them to your source, and then one of them is an enable pin, which is like a switch. So if you feed high voltage to that enable, by high voltage I mean the battery source, whatever you're putting in. So your voltage in, which is let's say 5 volts, also goes to your enable pin. That switches this LDO on, and then on the output you can put a divider, like with 2 resistors. You can make a voltage divider which will define what's your step down voltage going to be. and then you get that volt. So this is a high power LDO. This is about 1 amp LDO, which is really cool in that small a package. So let's put this aside. So you can have LDOs in your devices, and you can then cascade. And the more the LDO power, the more devices you can strap onto your project. So back to power. We have voltage and amps. When you multiply these two, voltage and amps, you get wattage or watts. So if I have a 1 volt battery, and that 1 volt battery has a capacity of 1 amp hour, Ah for amp hour, that means if I multiply this, it means that that battery or that capacity can give me 1 watts for 1 hour. So over 1 hour time, it can generate 1 watt, and then at the end of that, the battery is going to die. So this one over here, we can find the wattage of this by multiplying 3.7 volts times 25 milliamp hour, or 0.025 amp hour. And let's see what that is. Calculator. 3.7 times 0.025. That's about 0.1 watts. So this thing has 0.1 watts of capacity for 1 hour. But because it's a lithium-ion battery, it can either do 0.1 watts for 1 hour, it can do 0.01 watts for 10 hours, or it could do 1 watt for what would be a tenth for 6 minutes. I hope that's how it scales. So 60 minutes divided by 10 would be 6 minutes. Yeah. So, or 6 watts for 1 minute. So that's how power scales. High discharge. So the 6 watt for 1 minute is dependent on the discharge capacity of this battery. So lithium-ion batteries are usually capable of discharging much more than normal batteries. Normal batteries would not discharge that many times their amp hour. So the voltage would be the same. In this scenario, in the 1 watt scenario, let's find out what the amps is going to be like. So you have 3.7 on one side, and then you would need about, so 3.7 times watt is equal to 1. So 1 divided by 3.7. 1 divided by 3.7 would be about 0.27 amps. 0.27 amps is 0.27 divided by whatever this is, 0.025 is 10 times. So that's 10C. Now, there's this new concept called the C rating. It's called C rating. So lithium-ion batteries usually have a high C rating. Normal batteries that are the AA's and AAA's, they have a 1C, 1 or 2C rating. What that means is that if the battery says it's 25 milliamp hour, it will only be at an instant, it will only be able to give you 0.1 watt of energy at an instant. So if it's I'm trying to think of an analogy of a hose of water. So doesn't work. So if this in the C rating, you can imagine that the amount of energy that can come out at a time. So if I have to run this motor and it requires 1 watt if the C rating of this is 1, this motor will not be running at 1 watts. It will always run at 0.1 watts, because that's what the rating of this battery is. But because I know that this is lithium ion and the C rating is about at least 20, that means I can drop 0.5 amps out of this for sure, which is huge, which is, yeah, huge. It's about 2 watts. So that means I can multiply this 0.025 times 20, and then I get 0.5 amps. So if I have a load of 0.5 amps on the other side, I'll be running that at max, at full load, whatever that device is. It could be a big motor, big servo, but it will run for a much shorter time because this is a super slim battery. And then you know that if it has a capacity of 25 milliamp hour times 3.7, you only have about 1 watt for 6 minutes, or 2 watts for 3 minutes. So you can scale it like that, and that's basically how you work with power. Here we have a few solar panels. All right. Okay. So today we're gonna be hooking up. Next, we're gonna be hooking up the solar, this battery management module with this battery, and then see if we can get power out of it, and then we'll see if we can work with these film solar panels, because these are much more thinner and lower in profile than this thick one that is not even flexible. So that's what we're gonna do. So this one comes in your kit, and then these are extras if you want to go this way, where you can put something super flexible and super slim into your project. All right. First off, you want to start with soldering the battery terminals. Clean solder tip. Let's apply some flux, makes things easier. So I've done one terminal, and I'm going to do the next one. Okay, that's a big blob. Once that's done, we want to make sure that our battery still functions. We didn't break anything. Put the voltmeter on volt DC. We're reading a DC voltage. Conventionally, red goes with plus, black goes with minus. Usually these DMMs are smart, so if you flip them, nothing bad is going to happen. So you can see we have 4.1 volts. If you flip them, all it says, the DMM will tell you that, hey, your thing's flipped by putting a negative sign at your reading. So it says it's DC, but it says there's a negative sign before your reading. So next on, we want to read this board. So the board over here, let's get our tweezers. So you can see there's a negative battery terminal, there's a positive battery terminal, then there's your output voltage, which is positive, negative, and then over here you have your solar input voltage, which is between 0.5 volts and 4 volts. So there are two of those. Yeah. And that's also if you want to charge your battery with USB. That's for that. Let's zoom out a bit and see if we can solder some terminals onto this. I wonder if we can directly do that. Oh, perfect. So let's do this. Let's solder the battery directly onto there. So it says positive here and negative there. So this should just work. I'm going to tin the terminals. Going to put it face down. No, that's going to flip the terminals. So I'm going to keep this here, positive, negative. Okay, we have our battery in there. Let's connect a solar panel and see if that works. We use a wire stripper to get rid of these ends. And the other end as well. Start off by thinning the ends. So this is super helpful because you essentially deposit solder on the pin, and then when you merge it with any other pad that has solder on it, it sticks instantly. So our negative solar goes there. That was a bad joint. That's okay. That was a better one. And then on the other side, we have our solar panel. It says negative and positive. Is it working? We're going to do one more test. Connecting the USB. So it says charging. It's USB charge. And The wiring's done right, so the battery must be charging. How do we check that? We can check that by removing the battery for just a second. The battery disconnected. Battery pack, let me see. So that's good. We're getting 1.4 volts. So that means the battery is being charged. That's great. Let's solder that back on there. So now our battery is permanently being charged. And if we put an LED onto the output pins, which is here, it should light up. There we go. So that works. So we have our battery charging system here, and you can get rid of this thick connector. You can get rid of maybe the USB even if you don't need it. But this is a good board to have your project. It's slim. If you get rid of this connector, it becomes even more slim. It becomes almost as slim as the battery. And then this solar panel, you can replace it with these film type ones, which will make your project even more discreet. So next we're going to look at how we can merge these into there. Alright guys, so we're back, and what we want to do today, or more like right now, is we have this mini Arduino here, and essentially this is made up of this AtTiny85. So as you can see, we have an AtTiny85 here, and then we have one on this board there. So there are some limitations when you're working with this kind of a dongle system. Uh, there's some programs and some functionalities of this AtTiny that you cannot use properly. And so there are two ways of loading a program onto an AtTiny85. That is, we saw the one way in which you want to upload a simple program. So you can use a PWM pin, or you can use any digital pin, analog pin. Um, but if you want to use more complex sensors, so which we'll be looking into today, unfortunately, you cannot upload the program with the USB in this manner. So we're going to see how we can upload a program onto this, but not with the USB. And the sensor we'll be working with today is this gyroscope that should probably is in your kit as well. It's an GY521, very common. And here, so sensors usually communicate in many different languages. The one we looked at earlier is the digital in and digital outs. So a sensor will put a digital high or a digital low based on whatever it's sensing. But or even an analog out on whatever it's sensing. But this sensor here particularly speaks in has a data language. So it has a serial language. It means it has a stream of data, which is SDA, and then SCL, which is the clock. So using these two pins, there's a language that's being put out of this processor. It's not just a high or a low, because this gyroscope is doing a bunch of things. It's doing um, it's measuring many different values. So it's not just one or a zero. It's a whole stream of data that is going through the SDA and SCL pin. Now let's move on to here and see what the SDA and SCL pins are. I'm going to start recording. And so we're working with the AtTiny85, and what we want to see is what is this pin, what is the pin out for this IC. So AtTiny85, and then you type in pin out. So pin out, the term pin out usually gives us the results and what are the functions of all the pins of that particular device. So you can do an Arduino pinout, Arduino Uno pinout, and it'll give you all the pinout functions of what all of these devices do. Or you could do a pinout of this, what was this called, GY521, and then that too is going to give you what all these pins mean. If for instance you can't see clearly what these words are. So pinouts, we're going to open this pinout and open image a new tab, and we're going to see what the pinout of the AtTiny85 is. So again, we look at the dot from on top, and we see we have ground. So the numbering starts from the dot. So we have PB5, PB4, PB3, PB5, PB3, PB4, and on the other side we have 0, 1, 2, and VCC is the positive terminal. So we have positive terminal on one side, the ground on the other, and then these 6 pins are our outputs. Out of these 6 pins, which are your outputs, I think one of them cannot work because it's a reset pin, and that is the one over here, PB5. PB5, I don't think it works. I tried working with it, but I'm not sure. It can take data inside, but it can't put anything out. Yeah. All right. So we essentially have pin 2, which is PB3, pin 3, which is PB4, and then pin 5, 6, 7. We have 5 pins which can act as data pins. And here you can see in purple the timer pins. You have 3 timers on this. So you have 3 PWMs out of the 5 digital pins that we have here. Once pin 3, you can have a OC1B. That's a PWM pin. That's a PWM pin, and then you have a PWM pin on PB1 as well. The 2 pins we're looking for are the SDA and SCL pin, and then you can see here that's pin 7, which is SCL, and pin 5, which is SDA. So a lot of these functions are overlapping, but once you define one pin to do a certain function, it can't do something else. So one pin cannot be an SDA and be a timer. So it can do like perform one function at a time or be an input. I mean, in more complex programming, while the program is running, you can change the definition of a pin to something else. But in the more higher level stuff, or you could say in the more surface level stuff, you define one pin, and that's what it is. Okay. So now that we have an idea of what this pinout is, we want to see how we can program, or how can we connect this to the Uno, see if we can get some readings, and then connect this with the AtTiny85 and see how we can have some readings go from here to the AtTiny85, and then connect an LED or something to the AtTiny85 and uh, make it do something. Okay. All right. So here we have our Arduino. Here we have our GY521, and then we have our Arduino AtTiny85, and then we have the AtTiny85 on a board with a USB port. What we're going to do really quick first is we're gonna head out onto the website, onto the internet, and search for. Try to screen record. So new record. Cool. So whenever I want to search for something, I will just search Arduino and then that sensor, and then usually ends up there's a website that says how to hook up the sensor and how to what kind of code works on it, and if there's a it would also direct me to a library if there's a library for that particular device. So because we're working with a generic with a very generic sensor and a very generic SDA, SCL kind of a configuration, there's no special library, I think, that this device would need. And here you can see how it's hooked up. You have the positive and negative, and then you have the SDA, SCL. So you have four connections on this device. You can see here are the connections, and here's the code. So if the code is not there, then there will always be a specific link to a there would be a link to some library that you could load, and then from the library you can pull out a program. Nope. Nope. Okay, so we're going to paste our program here, and it's doing a lot of things, but what this program is doing is, first of all, it defines that there's a MPU, which is this sensor over here, and that has an address of 0x68. Then it's defining some 16-bit integers, which is big numbers. There's ACX, ACY, ACZ, TMP. TMP is, I think, temperature. So this is temperature as well. Cool. Gyro X, gyro Y, and gyro Z. Wire begin transmission to MPU. And MPU is this thing. So even if you put 0x68 down here, it will work. Write OX6B. I think this is like calling out a register saying, hey, start taking readings. And then end transmission true. Serial begin. We looked at serial before. So the reason why this is using serial is so that in the serial port here, well, the serial port's not gonna open up because there's nothing hooked up. But once we upload the program and hit serial monitor, we'd be able to see all of these readings. So in the loop part of the program, this is the meat of the program. So we're reading these 6 values, which is the ACX, ACY, ACZ. We're reading from the MPU, and we're storing it in these variables: ACX, ACY, ACZ, GYX, GYY, GYZ. And then in the next part of it over here, we're just printing all of this information. Yeah, we're just printing it down. And there's a delay of 333 milliseconds. And this is so that you have a slight delay after each reading. So if you reduce this, the number of readings per second is going to increase. So if you make, so right now this would average at about 3 readings a second. If you make this 10 milliseconds, that would be about 100 readings per second. Now in tools, we're going to go and select our board, which is an Arduino Uno, and we're going to hit verify. Verify is like compiling, and if it compiles, we're good. The sketch compiles. And what we'll do next is connect our Arduino board. We'll first connect our sensor to our board. And how we're going to do that is there are 4 pins here. That is VCC, GND, SDL, and SCA. And on the other side, we do the same. Now, if you look up Arduino board pinout, let's look that up and see. Arduino Uno pinout. Now let's go to images and see for a similar image like we did for the AtTiny85. Need a high resolution one. Something that's not super confusing. This is good, but low resolution. Come on. Okay, better. Open image in new tab. So if you look here, we can see all the pinouts. You have the power in blue. You have Arduino pins. And then we have the 80 mega pins. And here you can see that there's PC0 to PC5, but there's an SDL and SCA that overlaps with A4 and A5. So if your program has an analog read on 4 and 5, you can't work with SDA and SCL. So you can see how, again, we have some pin overlaps over here. Same thing over here, you have TX, RX, and you also have digital 0 and digital 1. You also have an SD and SCL up here. So I think it's the same as this. So it's PC4 and PC5 and PC4 and PC5. So you can have SD, SCL hooked up there as well. But within your program, you can't be reading analog values from A4, for instance, and also communicating with the sensor via SCL and SDA. You could, but that you need like high level. You need to program the registers, and it's more complex. So here, let's hook these wires up. You have power on this side, which is 5 volt and ground, and then SDA and SCL on the other side, which is A4 and A5. And let's connect the Arduino, upload our sketch, and it's done uploading. We're going to open up the serial monitor, and then we see every 10 milliseconds, we're going to see a reading show up. So let's say new line, turn auto scroll off so we can read each value. So you have accelerometer X, Y, and Z, and then gyroscope X, Y, and Z values. And then they're big values because you can see here it's like 17,900 something. They're like more like digital values, and they don't have a corresponding real value. You can always add a dividing factor and then make it so that it's like 0 degrees and between 0 and a 90 degrees plus, and then a negative 90 degree on the other side. You can do that. Okay, So now let's get rid of the serial print. No, let's keep it there. It's good for debug. I usually get rid of it because it's just clutter, but I'm going to hit Control and slash or backslash, and then it comments it out. So that means it's not included in your program, but it's just going to be there. And I'm going to play with some of these values. I'm going to define integer. I'm going to define integer LED. That's the name of the integer, and I'm going to give it pin 13, for instance. That's the pin over here. Now I'm going to give it 12. So that's a different pin. And in setup, I'm going to also say pin mode, LED, comma, output, and output. And down here in the loop, what I want to say is if bracket open, G, I want to pick X. So ACX is greater than 6,000, then do something. And what is that? It will be digital right LED high. And then outside of this, I'm going to put an else, so that if it goes below that, if it's below 6,000 value, do something else. Else digital right LED low. Okay, let's compile this. So this is going to do this again every 10 milliseconds because it's in the same loop. Let's verify. Oh, we missed a semicolon here. Verify and upload. So on our pin 12, let's strap an LED into there. There it is. Sacrificial LED, pin 12 and ground. So we can see that in this orientation, so now we know which is X. So as we bend this way, the LED turns on, and when we put it straight, it turns off. There we go. Next, what we're going to do is we're going to do the same program on this tiny one. All right. Okay. So we looked at how we could use the accelerometer and gyroscope to turn an LED on in the last tutorial. Right now, we're going to look and see how we can transfer that functionality down to this, which also means use the same methodology to transfer that functionality down to this, because essentially these two are the same, except that this has a board and this hasn't. This doesn't. What I'm going to be using to demonstrate this is I'm going to quickly solder a few cells, standoffs onto this board, and then so that we can quickly connect this jumper to it and disconnect it whenever we need to. So I will quickly do that. Or you know what? So I'm gonna put this in here. I want to do it in a way so that it can come out later. No, never mind. Just going to put this in here. No, I want it to be flush. The reason why I'm doing it on a board is that the mat underneath doesn't burn. So I got a few burn marks. You can get a high temperature mat as well. It's like a silicone mat, though that stuff doesn't burn. Okay. The other side, I'm soldering these 3 pins. These are our power pins. Alright, goody. Okay, so we have our power connected and we have our 6 other pins connected. So out of these, how we're going to program this is not through the USB. We're going to be programming this using this Arduino. And how that works is that you feed power to this, and then you feed a few pins to this, and then the system bypasses this chip, which is your receiver in this configuration. This is your programmer, or this is what sends information, and this is what receives it. And when you connect this board, essentially you're replacing this IC or this Arduino with this one, so that now whatever comes through the USB goes onto here, and then from here it bypasses this and it jumps onto this. So you're programming this with the Arduino. The wiring diagram, I'm going to hook up the wiring diagram so you guys can follow and not make any mistakes. So that would be positive and negative, which is 5 volt and ground. And then you have 10, 11, 12, and 13 on the Arduino. So I'm going to do that as orange, yellow, green, and blue. 10, 11, 12, and 13. So that's on the Arduino side of things. And on here, you want first positive and negative. You want 5 volt and ground. As you can see, we have the power pins, 5 volt and ground. 5 volt and ground. And here you want PB0, 1, 2, and 3. I think that's the one. No. So you want 5. PB5 gets connected to 10, which is orange. This. And then 0, 1, and 2 is 0 is yellow. 1 is green. I'll attach the image that I'm following. 2 is blue. Blue is PB2. Blue is PB2. Perfect. So that's the wiring diagram or the wiring hookup. Take a video of this, And on the other side, we have 10, 11, 12, and 13, and then 5 volt and ground. Okay. Uh, on the computer side of things, let's get into that. It's slightly different. You have to download a few boards. Let's connect this. Oh, before we do this, there's a step that I missed. We're going to instruct the Arduino. We're going to go to examples and look for Arduino ISP, and you need to first. So the first program you load. Okay, I need to do this again and record. So this is the image that I was following. Open image in the tab. So this is Arduino pin 10 goes to PB5, pin 11 goes to PB0. This is not pin 6, this is pin 12. Pin 12 goes to PB1 and pin 13 goes to PB2. That's the AtTiny85 here. Okay, now that we have that, we're going to open up our Arduino IDE. Here in Tools, what you'll have to do initially is go to Board Manager, not to Board Manager. You have to go to File. Again, I'll add the link. Cancel, close. Oh my God. I don't want you looking for stuff right now. Okay, we're back, and I want to go here to Preferences, and then in here I can select my boards. This is super small, but you can see I have like many boards. So adding a link here, I think this is the micro core. I'll add a link to this too. So when you add links over here in your board manager, you basically, it connects to many different board systems out there, many different Arduino boards out there, and then you can download and install new boards or make more chips compatible. So if I look for, I think DIY, so there's AtTiny DIY. So this one has AtTiny85 and all other ones available, and microcore. And microcores installed. I think we'll be using microcores for the Tiny 13 only. If I go to tools and then boards, this one is AtTiny core. We'll be using the AtTiny core. AtTiny core is installed from Spence Conde. That's the one we gotta grab. Okay, once we have that installed, we want to go to examples and Arduino ISP, pull that out, and all we do is connect our Arduino Uno here, make sure it's COM port selected, and hit upload. So this tells the Arduino that, hey, start programming to the thing that's hooked on to pin 10, 11, 12, and 13. Once that's done, you can close this. We can connect this to pin 10, 11, 12, and 13. And what we do next is tools. Now we select our board, which is AtTiny85. No bootloader. Let's see if this compiles. It does. Let's hope it uploads. It is uploading. And it's done uploading. What we need to change is that this LED is on pin 1, not pin 12, so that we get the same, so we can get the same effect. Okay, we're done with uploading the program to the board. What we want to do next is hook up our accelerometer and gyro and see if that works. That would mean we need a 5-volt and ground. How do we do this? And we need SDA-SCL. Let's look here. We have SDA. SDA is pin blue, and goes to 0, 0, and pin 2. That's our SDA and SCL. And next we need power and ground. I wonder if we do this. And then do this here. Are we getting power? Yes, we are getting power. And I'm gonna hold the ground with my finger. Not the best thing to do. Okay, maybe we should do it the right way. Get a breadboard. Connect positive and negative here. Oh, in fact, what am I doing? We're going to hook up 5-volt and ground onto this. 5-volt ground. And we're going to connect this to the USB. That will feed us power. Yay, it works. So it's super faint, but if you look at the red LED, as I move the gyroscope, it lights up and turns off. Lights up, turns off, lights up, turns off. In this very same way, in the 6-pin method, you can upload the code onto this tiny little thing and have the exact same functionality as here. The only difference is that this is much smaller to solder. Unlike this, you have big pins here. On this one, you probably will need to use really thin wires. I usually prepare something like this so I can quickly upload code onto a small chip like that. And that's our serial SDA and SCL tutorial. Thank you.